Welcome back to Material Atomics. My name is Nastya,
I'm Shiloh.
and today we want to deal with gravitational waves. Specifically, we want to try and fold them into our material conception of the universe. And to do that, we have to understand what are gravitational waves, how is it that we characterize them, and how they're different from light.
What's really fascinating is that the gravitational waves, whether you believe they are actually occurring or not, have been proposed for a long time by heavy hitters like Heavisides, like Poincaré, like Einstein. They emerge from these mathematical conceptions of nature, and they seem to reflect a lot of the same properties of the interatomic medium that light itself does.
I remember reading that they travel at the speed of light, which fits into our conception that the speed of light is a fundamental speed limit of the material, where it can't deform any faster than that. And if atoms are interconnected by these filaments, and light travels along the filaments are made out of a material that has a maximum speed of deformation. And that maximum speed of deformation happens to be the speed limit of light. And so the gravity waves have the same speed limit, suggests that they are also somehow a product of this filamentary interconnection.
But it gets even crazier because not only are they traveling at the same speed, but they also have the same bizarre transverse wave travel, right? And where else in the universe do you see transverse waves except for light? Well, you can twist on a material. If you have a bar of iron or a board, you can twist it and produce a transverse wave in it. That's the only way you can produce transverse waves. So something is being twisted that travels in the same material as light itself. We also see the same relationship where the speed of light is directly proportional to the frequency times the wavelength. So you start to add up all of these little pieces, and it gets pretty difficult to imagine that it's occurring in any other substance than that which is hosting light itself, which we propose as these radioelastic filaments.
But the big difference is the fact that light is considered electromagnetic radiation, so it's an atomic phenomenon where the twisting of the atom seems to be what is producing the radiation that we see. But with gravitational waves, they're not treated as electromagnetic radiation, they're treated as, deformation of space-time. Deformation of space-time in our conception of the world is pretty irrational, right? Because space-time is 3 dimensions of space and 1 dimension of time, so you're taking bodies and ideas and you're rolling them together and you're trying to make them do something, but that doesn't work. However, I think that you can look at space-time as being the matrix of filaments and atoms as they are connected to each other and the deformation that happens within that network.
It's like they're representing the connectome, right? Space-time is this connectome. It's a concept, an idea, but it's not. It's essentially treating the map as the territory. The territory is bodies all pushing and pulling on one another. The map is this thing we call space-time, which is a dynamic concept to describe how those interactions unfold.
It's the sequential cause and effect. That's what it has to be, right? Because a thing happens, and then there are consequences of that event, and the consequences of that event have to be propagated in some material. And so the simplest way for us to think about it is to imagine that the material that connects the atoms together is the material in which this propagation happens. And so when people talk about space-time, instead of treating it as something that's, purely irrational and absurd, I tend to imagine it's a really easy lateral translation for me, where, okay, they're talking about space-time, we're talking about the interconnection, the nodal interconnected architecture of the atomic web. Okay, so electromagnetic radiation like light is actually happening inside of the filaments. The gravitational wave is like bulk motion of the filaments.
All right, so I think this is where we move over and start imagining what is happening that is different in gravitational waves versus light waves.
Okay.
So under our model, and you should check out this video to get started on understanding our model of light, we have atoms whose shells have extended filaments, which are radially projecting outward from the surface. And these are evidenced by the radial distribution function of the electron, which says the electron can be found at any distance from the nucleus, actually. At any rate, these interconnections between the atoms alleviate discordance. How do we say? They alleviate the disequilibrium that forms when two atomic surfaces are in different states of freneticism. So one atom is vibrating at a different rate than another one that it's connected to. Light serves to equalize that surface motion, and that surface motion of the electron is defined by the concept of spin 1/2, which you can check out this video to see how we illustrate this idea of spin 1/2. But to simplify it, the outer shell of the atom, the electron, seems to be moving with this particular rotatory involuting motion, and light serves to transmit that motion from one atom to the next. Now, gravitation, on the other hand, is different. Gravitational waves seem to be relieving the imbalance in pressures on either side of an atom as it translates through space. So as you can imagine, when an atom moves through the room, like say when you walk into a new room, not only do you have to establish new connections to the objects around you, but you're also constantly putting strain on one side of the filament of your atom, that filament, and you're releasing some of the strain.
You mean like as you're moving forward?
Gravitational waves only appear during acceleration. So if you're moving at a constant speed, there's no gravitational waves. But as soon as you change something about your motion, now there seems to appear a disequilibrium between the tension on one side of your motion versus the other, and that has to get equalized in the nodes in the nodal network somehow.
It's kind of like the equivalent of a Doppler shift or something like that. Or a Doppler, yeah, it's a Doppler shift. Where
Doppler shift it just has to do with motion, whereas this has to do with acceleration.
Do you have insight on why it's acceleration rather than just motion?
My sense is that an object that is in motion is not under changing tension because it will form new connections to the atoms that it encounters at the same rate that it loses connections to the previous atoms. But if it changes its trajectory, it might all of a sudden encounter more connections in one direction than in another all of a sudden. And that tension mismatch has to be equilibrated somehow.
Okay, so you're moving through this network of filaments, and as you're moving at the same rate, you're encountering, there's some flux of filaments that you're encountering. That as you just move through a room, there's some rate at which you encounter them. And
I mean, you have to really simplify this to like this perfectly homogeneous room that has as many filaments in front of it as behind. Like it's an idealized room. It's like a universe, essentially.
Sure, yeah. So in this idealized room, as you move forward, the rate at which the filaments release behind you and the rate at which you're meeting them is roughly the same. And so there has to be something to do inherently with the speed at which you're moving. And that once you settle on a speed, that network can equilibrate to accommodate whatever speed you're moving at. But the minute that you start to accelerate, what you're doing is there must be a lot of inertia in the system, right?
It's directly related to inertia, which is, of course, the main evidence for gravitational mechanism in general. This idea that when you try to change a body, right, you change its position all of a sudden, you encounter a lot of resistance. And why is that? Well, because it's connected to everything and it wants to stay there. And when it's moving, it's also still connected to everything, and it's also departing from a lot of connections as well. But that change is what's important, which is felt as inertia, which is experienced as gravitational waves if they actually occur. And there have been many, many detections of them, and you can make of them what you will. I'm personally a little on the fence about some of these detections. I've seen some really good rebuttals about the noise filtering and so forth. But it stands to reason that they do fall out of a lot of the fundamental equations that we use to make the rest of our statements about electromagnetic radiation or anything else, including the basics of Maxwell's equations, which Heaviside developed, and Poincaré too. So I think they're worth thinking about, in particular because they seem to reinforce the overall paradigm that we've come to understand from all of the rest of this empirically derived mathematics.
So the occurrence or non-occurrence of gravitational waves, I think, is kind of a red herring, because if you have a filamentary network of the universe with nodal architecture in it, there must be the propagation of large-scale motions through that network. You can call them gravitational waves, you can call them whatever you want, but
Especially during acceleration, right? That's what's interesting. If inertia is a thing, and it's apparent, inertia is apparent, and inertia is due to the sudden disequilibrium of connectivity, i.e. during acceleration, which it is, and that's how we model it under our model of gravity, then of course there should be some wave propagation of that momentum as it's re-equilibrated, right? There's an oscillation as the tension is equalized, essentially.
yeah, exactly. So when we were talking about this before we started recording, we were talking about this in context of radio waves and the way that electromagnetic radiation seems to be on the level of the atoms, and radio waves are starting to head towards the direction of it being a collection of atoms that have to be generating and translating the wave.
That's worth a whole video, by the way, soon. We'll deal with radio waves and groups of atoms for sure. Yes.
But then you have the gravitational waves, which seem to be an order of multiple orders of size larger than the radio wave, because we were looking at wavelengths, and these wavelengths are, I mean, the range that's given is crazy. It could be up to what?
The size of the,
The size of the universe.
I mean, they're hundreds of kilometers, yeah.
Hundreds. The thing that comes up when you first search it is some page that claims 600,000 kilometers, I think, for the wavelength of these waves. And so they're massive scale deformations that are categorically not the same as the atomic deformations that you get when you're looking at light and electricity and magnetism.
I think that is potentially due to the fact that they're so weak that we're only observing huge events. But if our theory plays out, you should be able to see single atom gravitational waves as well. And I would expect that fusion itself would be similar on the atomic level to, say, neutron-star merger at the macro scale, where, yes, you can see these big, powerful, low-frequency waves with the neutron stars, because there's gazillions of atoms, but the phenomena itself is an atomic phenomena, which is why we're even talking about it here at Material Atomics.
So the bottom line here is that gravitational waves are observed and predicted. There is some controversy as to whether or not they have been observed, but on a theoretical level, in a nodal architecture universe, a transverse wave that travels at the speed of light and is due to acceleration of enormous bodies seems likely to be theoretically possible. And if it is possible, the reason for it is that acceleration causes a differential equilibration in the nodal architecture that you can detect at a distance, because that equilibration propagates outwards in a similar way that waves on the surface of a pond propagate outwards when you drop a pebble into the center.
I would even go so far as to say it's a prediction of our model that gravitational waves occur, for sure. And if we're wrong about that, then we're misunderstanding something big here. And I think that's how Heavisides thought about it too. And I think that's how Einstein thought about it too. They didn't have any observations of the things, but they fell out of the theory. And that's kind of what we're looking at here. Another point that I didn't get to mention that I want to say before we leave, the gravitational waves are measured and interpreted in terms of the change in distance at these detectors as the wave passes through them. So space-time is distorted such that distance expands and contracts as a wave. Gravitational waves are detected using these long hallways, essentially, which are said to change in length. They expand and contract as waves. This is how gravitational waves are observed. What's really interesting is that while I would never suggest that the fabric of reality itself is being distorted, it kind of is, because if these filaments are in fact varying in tension, then it would make total sense that the light distance, that is the amount of distance covered by light, which is just a deformation of a medium, would vary as the material properties of that filament changed, i.e., as the guitar string is under less tension, it's going to wobble differently, and the distance measured as a result, if you are assuming that the distance is constant due to the constant speed of light, then of course the distance falls out to be shorter or longer. In reality, that speed of light is actually variable ever so slightly, and that's what's happening because the material properties of the filament under tension are less or more depending on the amount of tension it's under. And because this entire model of gravitational waves depends on varying tension, really equilibration of tension in an accelerating mass, from an accelerating body, you have changes in measured light distance as a result.
So does that also mean that the theory predicts that inside that hallway, as the wave is passing through it, that you would see effects in the light somehow too? Like the wavelength of light would change as
it does, because it's measured with light. That's, I guess, what I'm trying to get at. The way they measure the length of those hallways is by having a standing beam of laser light. And as the thing gets out of phase with itself, they say the hallway shrunk. And I'm saying, no, the filaments change their tensile properties in a wave-like fashion along it, which affects the waves of light in the same filaments.
Whoa, I like that. Cool.
Anyways, let us know what you think. We're obviously just beginning the brainstorming phase of this aspect of material atomics. We really need your help, so share our conversations with your friends. We really want to see you over at Discord, giving us ideas, helping us figure out where to go with this next. Anything is open game, really, as long as your ideas concern bodies in action, doing things to other bodies. We start with the atom or the subatomic fibers of the atom, but give us your ideas with that in mind, and we're very open to it, and we want to develop this and hear more. And we really need you to talk to us and give us input and spread these videos around. YouTube's not about to do it anytime soon, so we need your help.
Leave a comment. Tell us what you think. We'll see you next time.